thank organizers for inviting me here. And I'm going to tell you about actually two topics. Both are related to solitonic excitations. One is in heavy ion collision, and the other one is in ultra cold atomic gases. So to be more precise, first um, I will tell you about solitonic excitations in nuclear collisions, and then later about some metastable Larkin-Ovchinnikov droplets, which we called ferrons in ultra-cold Fermi gas. So let me start with this very general slide concerning pairing correlations in nuclei. So we know there are pairing correlations. So we have some information about the strength of the pairing correlations, and there are experimental data supporting the existence of pairing. Like, for example, in high spin physics, there is this famous backbending phenomenon concerning the moment of inertia. And we know also that for large amplitude nuclear motion, we need pairing for the system to actually undergo, like, for example, fission. The pairing is really crucial. But the question is whether there is really a phase, or these are simply correlations. So this is the question that people wanted to answer for many years. And in other words, if there is a phase really, so are there phenomena that actually probe the degrees of freedom of the phase, like, for example, the phase of the pairing field. So the famous example is the Josephson junction effect, that we know that the current is flowing due to the phase difference between the condensates. And in nuclear physics, people were searching for the similar phenomenon, like in Josephson junction, and that already started a long time ago, like in the late 60s and 70s. And there were some experimental data concerning enhanced neutron pair transfer in the collisions, but they were not very conclusive. There is very recent paper, very interesting one, which actually look for the manifestation not on the normal DC Josephson junction, but rather AC Josephson junction, because authors realized that actually there is a different energy of a neutron pair in two colliding nuclei. So that actually gives rise to the oscillation of a Cooper pair between colliding nuclei. They identify that during the collision process of this tin 116 and nickel 60, there are like three oscillations of the Cooper pair should occur during the collision, and that gives rise to the change of the proton distribution, and that in turn gives rise to the emission of gamma radiation. And they actually calculated the energy of gamma radiation, and surprisingly, they got an agreement with experiment. So if this is true, this effect should be visible also in other reactions. So now we are waiting for other reactions where this effect can also be seen. But this is not the only case that we can where the phase of pairing can manifest itself in a nuclear reaction, because as we know from ultra-cold atomic gases, we can have a so-called weak coupling. So we can have two condensates and a barrier between them and the tunneling process, which gives rise to the Josephson effect. But we can do something different. We can change the phase of one part of the cloud and with respect to the other part, and merge them, which will generate a strong coupling between condensate, and the effect will lead to a different result, will generate the solitonic excitation, which will eventually decay. That was experimentally observed in several papers, and they identified even decay pattern. This dark soliton that was created decay into 5-soliton vortex ring and vortex line. We actually repeated this. We actually used our approach to find that indeed we can reproduce this decay pattern. So the question now is, can we see something similar in during the collision of atomic nuclei, and what would be the possible manifestation of such an effect? So let's imagine we have a similar situation. We have two nuclei, and which are paired. So they have non-zero pairing, and then we change the phase of one of the nucleus and we collide them. So what is going to happen, and what would be how the dynamics of the reaction will change, and what will be the observable consequences of such collision. So from a very basic consideration, we can if we take the Ginzburg-Landau approach, we know that if we connect two superconductors differing by phase, so in the junction between the superconductors, the energy will be stored. That this energy depends on the sine square of the phase difference, half of the phase difference between these two superconductors. So in this case, we expect that these two nuclei, when they collide, so there will be a kind of solitonic excitation appearing between the colliding nuclei, and part of the energy will be stored in this soliton. Of course, so if one do a simple exercise and substitute to this formula some typical quantities related to atomic nucleus to find out what is actually the order of this energy, one can find that this is of the order of 30 MeV, which is actually quite large quantity. So now the question is it really the case if we apply more microscopic time-dependent theory? So this is what we did. So we use time-dependent Hartree-Fock-Bogoliubov. This is how we call it in the nuclear physics approach, with the density functional that is usually used for nuclear studies, and we perform this collision and to see what is going to happen. So if we took first non-realistically very heavy nuclei like plutonium-240. So these are what you can see on the left. These are snapshots from collisions. On the left row, you can see the density distribution. On the right, you can see the magnitude of the pairing. And as you can see, in the case of the collision with the difference between condensate equal to pi, there is kind of a solitonic excitation that appear between colliding nuclei, which is not going to appear when we have zero phase difference. So now these two nuclei are very heavy, so they merge and then they separate. So then we can actually calculate the kinetic energy of the fragments as a function of the phase difference. And as you can see on the right, this is what we get. The total kinetic energy is actually larger when we collide the nuclei with a phase difference equal to pi as compared to the phase difference equal to 0. So what does it mean? So these nuclei collide, part of this energy, and if the difference is equal to pi between the condensate, part of the energy is stored in the junction and then released during the reseparation, and that gives rise actually to this enhanced value of the total kinetic energy of the fragments in the case when we have phase difference equal to pi. And as you can see, this is actually very similar behavior to this sine square behavior predicted on the basis of the simplified Ginzburg-Landau approach. So, of course, in nuclear physics, we cannot control the phase of the pairing field. So at the end, we have to average over various phase differences of colliding nuclei. But the thing is whether the effect which will lead to the effective enhancement of the barrier for capture of these two nuclei, whether this effect is really large and can be somehow detected experimentally. So we did our calculations for medium nuclei. So zirconium 90 on zirconium 90. First, we used the simplified approach that we disregard spin orbit term, which we thought is not important in this case. So for these studies, as you can see, we get, so this is on this plot, you can see the energy, the minimum energy for capture of these two zirconium 90 nuclei. And as you can see, this minimum energy increases if the phase difference increases. So the difference between the minimum energy for capture of these two nuclei between these two cases, when the phase difference is 0 and pi, is about 30 MeV, which is again huge. Even if we average over all possible phases, it still gives us 10 MeV enhancement of the barrier for capture of these two nuclei. So that was very surprising result. Later, Guillaume Scamps actually published a paper when we took available experimental data for cross-section, and he analyzed this data, and he found that indeed it looks like the effect exists, although it's much weaker than we predicted. So therefore, we decided to repeat the calculations, but now with really the full functional, so including even spin orbit term. And we took one of the most popular functional, SKM star, includes spin orbit term, and this is what we get. So we get the enhancement of the barrier of the order of 6 to 9 MeV. So somehow, indeed, the spin orbit term turned to be actually important here. So it decreases the initial change of the barrier. So one interesting outcome of these studies can be seen here. So if we take, what is going to happen if we take these two nuclei, and in one case the phase difference is 0, and the other case the phase difference is pi, and we collide them just below the barrier for capture. So at this, these are snapshots from collisions at the same energy, just below the barrier for capture. So as you can see, there is very different dynamics in these two cases. So in the case when the phase difference is 0, a nice neck is developed between two nuclei, although they are separate. They are really forming for a moment compound system. And in the case when the phase difference is pi, due to the fact that there is this solitonic excitation, which gives rise to the additional repulsion between the fragment, the nuclear density practically do not touch each other. And as a result, if one calculates the excitation energy of the fragments after the separation, there's a huge difference between this case and that case. So as you can see in this column, the excitation energy of these two fragments in the case of 0 phase difference is more than 30 MeV, whereas here is much lower. We looked at we calculated this as a function of the pairing strength. The pairing strength was of the order of 2 MeV. That was more than 10 MeV. Excitation energy was 10 MeV smaller. If we increase it to 3 MeV, then the excitation energy dropped down to 8 MeV. So it's really a huge difference in the excitation energy of the fragments, depending of the mutual phase difference between colliding nuclei. So now the question is how this effect can influence the dynamics of nuclear reactions, and this is what we are currently looking at. So we would like to look in particular for the synthesis of super heavy elements and see whether the pairing dynamics, which was completely ignored to date in studies of nuclear reactions, how this can affect the cross sections for the super heavy element synthesis. So this is a long range plan because it required to make a lot of studies. So this is one part. So this is one part of my talk, and the other part is on something slightly different. So this is related to the old question concerning the existence of the Larkinov-Chinnikov phase. This is something that people are looking at for a long time, and in ultra cold atomic gases, it is expected that there is some region of the spinning balance for which indeed Larkinov-Chinnikov phase can be energetically favored. That was a paper by Aurel and Michael a couple of years ago. The experimental problem, as you know, with this Larkinov-Chinnikov phase, that if we use the harmonic trap, that's this Larkinov-Chinnikov phase will occupy, if it exists, it will occupy a relatively small volume of this trap, and it's difficult to detect. So the flat traps are really needed to solve the problem whether the low phase exists or not. But we look on this. We looked at this problem from a different perspective. So we consider the different situation. Suppose we have a spin unpolarized gas, and then we apply locally a spin selective potential, which will locally break Cooper pairs. So what is going to happen? Is this perturbation that we locally apply to the system, will it be stable or that will decay? So this is what is going to happen. I can show you here. So on this, this is what you can see here. Is what you can see here is the magnitude of the pairing field, and below is the polarization. So as you can see, when I'm applying the potential which polarizes the system here, then I'm breaking pairs here, and then at some point I'm switching it off. Okay, I switch the potential off, and this is what is going to happen. I created a stable object which has a very peculiar phase pattern. So as you if you make a section through this object, so the pairing gap is going to 0, and it's changing sign, so the phase changing by pi, and then it's the same is happening here. Okay, so this object seems to be surprisingly stable. You can do various things with this object. You can collide them. You can stretch them, and it still does not lose its identity. So we found the stability of this object is actually related to the fact that the polarization, which is concentrated close to these nodal lines. So in this nodal region, the quantized Andreev states appear, and these quantized Andreev states are responsible for the stability of this system. So let me. Okay, so if you look at the spectrum of states inside the gap of this object, these states are plotted as a function of angular momentum, because we have a spherical system, so we have an angular momentum. It's a good quantum number. So these states located in the nodal region, they form a flat band located at this energy, which is related to the difference of chemical potentials. Okay, okay, I can show you also that we can collide these objects. They can merge, but still, as you can see, the structure of this object is still conserved. So after merging, so again, what is happening? The larger object appear with again the same structure of the pairing field. So the pairing field changes phase inside, and there is this nodal area that appears here. The fact that Andreev states are localized in the nodal line is also responsible for an interesting property of this object. The fact that we cannot accelerate this object in the superfluid with, we cannot exceed a certain critical velocity. So if you look at this plot, so we were dragging this object using external potential, and then we were releasing the external potential. And as you can see, the final velocity of this object was increasing to some extent. And then at some point, we reached the value which we couldn't accelerate this object above certain velocity. So the question is, what is this critical velocity? What is it related to? Okay, so it turns out that accelerating this object will perturb this Andreev states inside the impurity, and there is a certain critical velocity related to the velocity in which the lowest Andreev state reaches the zero energy. At this point, this object becomes unstable. Okay? And this is also the reason why we cannot accelerate this object above this particular velocity, which is related to the chemical potential difference. And the chemical potential difference is related to the polarization, and the polarization is related to the radius of this object. So the larger object can move with larger velocity, smaller object can move with smaller velocity. So this is what we found. And an interesting consequence of this fact is that we cannot produce this object, which we call ferron, in the vicinity of the vortex, because the vortex produces the flow. And if we are trying to generate this object close to the vortex, this object, as you can see, will disappear. So this is due to the fact that if we are close to the vortex, the velocity exceeds this value and the object becomes unstable. So this is so we call this object ferron because it's short term. We could call it Larkinov-Chinnikov droplet, but it's longer because it has the structure which is similar to Larkinov-Chinnikov phase, but it's just like a droplet. So the question is whether this can be somehow detected experimentally. It's what we discussed for already more than a year with the Florence group. So maybe finally we'll get some convincing proof that such object can appear. And this brings me to the last very preliminary results that we did. This is my last slide. So this is now something different. We look for. So we were trying to find out what is the structure of the system as a function of polarization. So in our time-dependent BDG or time-dependent, not time-dependent, but in our Bogolivo-de Gennes approach, or in our superfluid local density approximation that we are using. So this is what we found. So if the polarization is small, we usually end up with a bunch of ferrons. Then if we increase the polarization, the system, the structure becomes more complex, but it's not like ordered solid like Larkinov-Chinnikov. It's usually something that is disordered. Only when we increase the polarization, really, you can see something that looks like something which is close to the Larkinov-Chinnikov. So the question is it really need to be something ordered like a super solid, or it's rather like a liquid crystal? So because the energy, if we compare energies of these structures, various structures, so we compare this disordered with this ordered or this, we got a very small energy differences. So it looks like we have a plethora of various minima corresponding to various structures. Most of them are actually of this type, then on the ordered type. So this is an open question. So we did this calculation in 2D, but in 3D, qualitatively, everything looks the same. So I would like to finish here just to give you an overview about other topics that we are studying using the approach that I was showing you. I would like to finish here. Thank you.
Great. Thank you. Questions from the audience?
Just to be sure that I understood the one point that you commented. So when you have the collision, you mentioned that you can change the phase of a nucleus. How you can change the phase of a nucleus?
Experimentally?
Yes.
No, I cannot.
Okay, so you can just do this.
Yes. I can change the phase in the theory. Experimental, I have to average. Okay, so I have the average information about the difference.
You mentioned at a certain point seeing flat bands. Does this have anything to do with the flat bands that you see in twisted bilayer graphene, or is this a completely different thing?
Maybe it's related to the peculiarity of Andreev reflection. So there may be some relation. So flat band means essentially that the system, the particles can hardly move, right? So and this is what Andreev reflection tells you, because if you have a scattering, the particles reflected as a whole more or less in the same direction, so it can hardly move actually. So it's in that sense it's related to that. Mm-hmm.
Questions from the audience online?
So I have a question. Can you hear me?
Yeah, go for it.
Okay. Thanks, Piotr, for a great talk. I have first, from a practical perspective, is a two-dimensional calculation like a BDG computation for you, just an easier version of a 3D, like, you know, or
Yes, yes.
is the physics that goes into it
Well,
messy?
well, both. I mean, experimentally we can consider 2D systems, so it's not a problem. But of course, it's computationally easier. So.
And that's why I'm asking, because the law of, is that why it's, you know, maybe there's a signature in 2D, it was easier to spot, like you can do a, you know, finer discretization, or could you like explain why 2D versus 3D, or is that the physics driving it?
But physics driving of what?
Of, you know, there's no clear law of signature in 3 dimensions, right? I mean,
Yeah.
any investigations have taken
Yeah.
place, but, you know, there's no clear, you know, smoking gun.
No, so we did 2D because we wanted to do systematic calculations of various structures. So it the computational aspect was important to us, but we did also some calculation in 3D. It's not much difference qualitatively between 2D and 3D. I in particular, well, as I didn't notice.
Okay, this is interesting. Okay, thank you.
Related to the previous question, does it mean that in 3D you can also have a spherical ferron?
Yeah. Okay, so ferrons, the calculations for ferrons. So these studies, the dynamical studies, were done in 3D. So it's really spherical ferron. So 2D is only this last part. So this plot is 2D, but all the others. So all that I was showing you concerning creation of this ferron, that's full 3D studies. Yeah.